All right, let's go ahead and work a couple problems in finding the average value of a function of two variables over some region of the xy plane. Let's take this example, maybe I'll call it example 1 here. Find the average value of z equals f of xy over the triangle with corners 0, 0, 2, 0, and 2, 4. How would you start this problem? Probably you would do the following. You would draw the xy plane and try to get a grip on this triangle here. Okay? Let's see, we've got the origin here, 0, 0. And then we have, let's see, the point 2, comma 0. Let's say it's over here. Doesn't have to look perfect or anything. And then we've got what? The point up here, 2, comma 4. Okay, like all my drawings, they are imperfect. Okay. There's a triangle. That's right, x and y here. Alrighty. Now, what we want to do here, so we're integrating this function xy over this triangle here. Okay, let's go back and think about, remember we were calling a z bar, not a vector. We'd be performing this, the double integral of f of xy dA over the triangle which we're calling R. And then down here, we'd be dividing by the area of the triangle. That would be the double integral of over R of dA. Alrighty, let's go ahead and think about the numerator here first. Let's set up the limits of integration. Okay. Now, this isn't particularly going to matter which order we integrate as far as, ease of calculation here. So I'm going to go ahead and just do the following. I'm going to integrate in the y direction first. So let's go ahead and draw our picket this way. So we'll be integrating up like that. Now let's see. My function is xy. I'm integrating in the y direction first and then the x direction. Okay. Leave a little room here. I'm going to be doing the same thing down here. Okay. Where is y going from and to? Well, regardless here of which x value I have in this interval, y is always going from what? 0? And then what? Up to this line. Now wait a minute, we need to know the equation of that line. Let's go ahead and do that mentally. Because it goes through the origin, it's going to be very easy. We could just say y equals 4 divided by 2 times x. 4 divided by 2 is 2. So that's y equals 2x, as you can see here. I suppose I should throw this in here also. That was our line, x equals 2. And the x-axis, we know what that is. I'm not going to label that. I've labeled enough, I think. Anyway, so y is going from 0 up to 2x. Okay. Now project this thing down onto the x-axis where x is always going from 0 to 2. And then the same thing would be happening here. Now, down in the denominator here, if you didn't want to compute this double integral, you guys easily, in your heads, could compute what? The value, because it represents the area of the triangle there, which you can do in your heads. But I'll just go through the motions for the sake of completeness here. Okay, just so we see this one time. Let's go ahead and work this guy out. Okay. I'm going to make another statement. Z bar, okay, integral from 0 to 2. Let's see. I'm integrating out y. Okay, you guys see I could actually factor that x outside of this integral. I'm integrating y. The integral of y dy, that would be 1/2 y squared. Okay, so I've really got here 1/2. That x factor remains y squared, and then y is going from 0 to 2x dx. Okay. Down here, I will do something similar here. Integral of dy was just y, so y is going from 0 to 2x dx. By the way, this is just the way I like to write it here. If you guys want to write these as totally separate calculations rather than making this statement about the average value of z bar, which is not a vector, you could do that, separately if you want, if you dig doing that. Okay, let's do a quick mental calculation here. Okay, I've got 2x, which is being squared when it's punched into y here. That would be what? 4x squared. Half of that would give me what? 2. So it looks like we got, with that other x there, 2x cubed up there, dx. Okay, at 0, it's 0, so I didn't pay attention to that. Here, if I'm going to do this, I'd be integrating what? 0 to 2. That would just be 2x dx. Okay. Alrighty, let's keep going. This is easy, just use the power rule. 2/4 x to the 4th going from 0 to 2. That's upstairs. Downstairs we've got x squared going from 0 to 2. And let's do a quick mental calculation. This looks like what? Half of 16, doesn't it? Okay. Also known as 8. 2 squared, that's 4. Check, we got 2 for our average value of z in this particular problem. Okay. In example 1, we could have computed the area of the triangle using elementary geometry. Also, which you guys know, let's go back here for a second. Our region was this triangle. 1/2 the base times the height. The base, you can see, is 2 units. The height is 4 units. 1/2 of 2 times 4 is 4. Okay, so that worked out for us. That would be a perfectly valid way of doing it on such a simple region. It's good to see it this way once in a while, though. Let's go to an example 2. Okay, so for my second example, example 2, I guess I can call it that, but it's actually problem number 24 in your book. That's just something I'm going to illustrate here in this particular problem. Find the average value of f of xy equals sine x cosine y over the region bounded by these. These are what? Vertical lines, and these are horizontal lines. What sort of region are we looking at? Yes, these are all constants, so this is a rectangle in the xy plane. So we're integrating over a rectangle. Okay, so when I start a problem like this, I think I will take advantage of this rectangular situation. I'll write the following here. The region, which I'll call R, like usual, is a rectangle. Make a statement here of area equal to, let's see, the larger x value minus the smaller x value, the larger y value minus the smaller y value. That looks like what? Pi. That looks like pi. So the area of that rectangle is actually pi squared. So that will be going in the denominator of our expression for, let's call that z, for z bar here. Okay? So let's go ahead, do the following. We could say z bar is 1 over pi squared times the integral over the rectangle sine x cosine y dA. Now, because this is a rectangle here, we can write the following here. Let's say I'm going to do, since I have started leading with x here, I'm going to lead with x in here. You guys see x is going from 0 to pi. And now y going from negative pi over 2 to pi over 2. Sine x cosine y dy dx. So I would actually be working out what? This inner integral first, integrating with respect to y, the way I've written it here. Okay? And that inner integral, do you guys see I could actually do what? I could take that sine of x outside that inner integral. And I've mentioned doing this many times, but let's actually write it this time, just to illustrate something here. Okay, I'll take that sign out, and I'll use parentheses here. On the inner integral, okay, so this is what we're looking at. And then once I get done with this thing, I would integrate that with this. Okay, I would have this as a factor multiplied on the sine of x, and then I would integrate with respect to x. But notice in this particular example here, what kind of an object is this right here? The integral from minus pi over 2 to pi over 2 of the cosine of y dy. This is a number, right? This is a number. That's just a constant. It's not even a function of x. So you guys see I can actually bring that outside the integral. Okay. Now usually I bring things outside the integral in front. I'm actually going to put it behind here. Okay, I'll put it at the end. So that z bar is 1 over pi squared, the integral from 0 to pi sine x dx, and that's being multiplied by this other integral. So you guys notice in this particular case, because my radicand could be written as the what? The product of a function of x and a function of y alone, and I'm integrating over this rectangle, unlike our previous example, I can actually break this into what? Just the product of two separate integrals, one involving x and one involving y solely. Okay? All right. So remember, we can do that sort of thing in these situations here. What's the antiderivative of the sine? How about negative cosine? So we'll go negative cosine of x from 0 to pi times, let's say antiderivative here would be what? Sine of y. Going from negative pi over 2, pi over 2. All right, let's do some evaluation here. So that's 1 over pi squared. Let's see, the cosine of pi is what? Negative 1. And I'm negating that, so I get 1. And then I'm subtracting what? This evaluated at 0 is 1, so that's negative 1 I'm subtracting off there. So there we go. Sine of pi over 2, that is 1. Subtracting from that, the sine of negative pi over 2, which is negative 1 also. And everybody sees I get 2 times 2 is 4 over pi squared for my average here. All right. Okay, let's go ahead and work one last average value problem here. This has example 3, I guess is what it would be. Find the average value of z equals f of xy equals x squared e to the xy over the triangle here. This is the triangle below. It's bounded by what? The y-axis, the horizontal line y equals 2, and the line y equals x here. I'm going to note, since we're finding an average here, I need to find the area of the region. I'm going to just do that mentally. It's a triangle, so it's 1/2 the base times the height. The height is what? 2. The base would also be 2, so it's 1/2, 2 times 2, so that's 2. So that will be the denominator in our expression for z bar, okay? So we're going to be taking half of the following. I'll be taking the double integral over the region I'm calling R, okay? F of xy, so that would be what? X squared e to the xy. Now, if you guys go ahead, before I write anything else here, you might think about the order of integration here. Would I actually want to integrate that in the x direction first or the y direction first as far as ease of integration? Okay, you guys can stop and pause here for a minute and give that a think. Okay, I'm going to explain here what we actually want to do is integrate in the y direction first. I'm not saying it isn't undoable if you integrate in the x direction first. I'm just saying it's probably going to be a lot more problem for us. Let's go in the y direction first. So I'm going to go like this. Okay, so that's y. where's y going from and to? Okay, so we're going to be going in the y direction first, so let's go like that. Y is going from what? X up to 2. Remember, y would be in terms of x here, so we get a numerical answer in the end. Project that down onto the xy plane. X is always going from what? 0 to 2, it looks like. Okay, so that would be our expression here. We want to think about what's happening right here on this. On that inner integral, I can actually bring, again, if you want to write this as a separate integration, a partial integration, and work that rather than doing it all at once like I'm writing it at once, that's okay. Okay, but I'm just going to go ahead and do it this way. I can bring that x squared out, okay, and I'm integrating from x to 2 e to the xy dy and then dx, you see? Now I need to consider what's going on right here in this integral here. My substitution would be the exponent u equals xy, and then du would be x times dy. Okay? All right? So what I'm going to do is actually put an x out here and a 1 over x out there. Remember, I'm integrating with respect to y. X is acting like a constant, so I can treat it like that now. Usually you would think about that, you know, moving a variable in and outside of an integral sign is a no-no. But this is only a partial integration here. Okay? So I've really got the integral of e to the u du, so this becomes 1/2 the integral from 0 to 2. X squared divided by x is x. Here this would be what? E to the xy, and then y is going from what? X to 2. Oops. And then dx. Okay. Alrighty. So far so good? Okay. Let's go ahead. We're going to substitute this in here. Y is 2 and y is x. Before you try that, maybe you should try this. Perform a partial integration on e to the xy with respect to y, and you would indeed get what? X e to the xy. Okay, so that checks there. All right, let's keep going. All right, so we've got z bar is equal to 1/2 the integral from 0 to 2. Okay. X times e to the 2x minus x e to the x times x, or x squared, and then it's going to be dx. Okay? All right. I'm going to break this into 2 integrals. And we're going to think about how we can integrate each one separately. Of the 2 integrals, which one is going to take more work? Okay. It's actually the first one that's going to take more work. The second one's going to be fairly easy with a substitution. So let's go ahead and consider this thing. I'll drop the half out front for now. You want to think about what technique you would actually use to integrate this thing. Can you tell me? Okay, do you know? Maybe you want to work that out separately. Go ahead and pause the video. Okay. All right. The answer is integration by parts. So I'm actually going to have u equal x. That would mean du equals dx. Okay. Remember Lyautey? dv equals e to the 2x dx. Integrating that, v would be 1/2 e to the 2x. Take any antiderivative there. Okay, make a quick mental double check. Yep. So this ends up being what? uv minus the integral. Oops. Well, the way I'm going from 0 to 2, I might as well put that in. Minus the integral from 0 to 2. U dv, v du. Okay, so this is going to be what? 1/2 e to the 2x dx. Okay. These are x values here, so you guys think about what's happening here. We would get what? 2 over 2 is 1, e to the 4. Okay. At 0, this thing's 0, so we've got that. Okay, how about this integral? Is this hard? Not at all. This is actually going to be 1/4 e to the 2x. Okay. She uses substitution. U equals 2x, and that would be easy to compute there. And what do we have here? E to the 4th minus 1/4 e to the 4th minus, let's see, at 0, that is actually 1/4 e to the 0, which is really 1. So we get 3/4 e to the 4th plus 1/4. Okay. It's okay for that part. Don't forget we're going to take halvesies in the end on this too. Let's go ahead and work out the second integral here. Okay, not good. All right, let's work out the second integral. This one's actually not hard at all. 0 to 2 x e to the x squared dx. Okay, use a substitution like w. dw equals 2x dx. So the x dx is actually half a dw. Okay. And then I've got what? E to the w. W is the square of x. X is going from 0 to 2, so that means w is going from 0 to 4. Okay. So that's 1/2 e to the w from w goes from 0 to 4 equals 1/2 e to the 4th minus a half e to the 0 being 1. Okay, now what we're going to do, we're going to take the difference between these two results, and don't forget, I'm really going to be what, taking half of that. These halves running around everywhere. So I've got this 3/4 e to the 4th plus 1/4 minus 1/2 e to the 4th minus a half. This is for my z bar, my average value of z, so I'll make a statement there. Let's see. So I've got 3/4 minus a half. I think that's 1/4. So I've got 1/4 e to the 4th. Taking half of this. 1/4 minus negative a half is plus 3/4. Okay. And I'm going to be taking half of that. So it looks like I have e to the 4th plus 3 all over 8 for my z bar. And there's my final answer.